Wastewater from food processing industries contains a very complex mixture of contaminants, from large solid debris, suspended particles to dissolved organic compounds. If discharged directly without any treatment, this wastewater will cause serious damage to the environment and downstream equipment. This is where primary wastewater treatment comes in. Primary treatment is the first stage in our wastewater treatment system, focusing on removing floating, settlable, and suspended solids before the water enters biological treatment. Think of it as a preparation stage. The cleaner the water entering the next process, the more efficient and cost effective the entire system becomes. So, what does this stage actually reduce? Primary treatments help lower COD, BOD, TSS, and TDS levels, and beyond that, it also minimizes operational risks such as equipment damage, pipe clogging, membrane fouling, and environmental pollution. In short, it acts as the first line of defense that protect all downstream processes. There are four unit processes in this stage, occurring in this order. The first is core screening, using bar screens to capture large solids right at the inlet. Bar opening range from 20 up to 150 mm, protecting downstream pumps and pipes from blockage and abrasion. Next is fine screening, which catch smaller solids that pass through the core screen. For example, fibers, fine food scraps, and stringy materials. Opening size is at the range of 1.5 mm down to as fine as 0.001 mm for microscreens. Flow velocity is kept above 0.3 meter per minute to prevent clogging, and this step significantly reduces TSS and prevents fouling in advanced treatment system. After that, the grit chamber removes heavy inorganic particles such as sand, gravel, glass fragment, and metal flakes that the screen cannot catch. Removing this early reduces equipment wear and prevents sediment buildup downstream. Finally, primary sedimentation, where gravity does the work. The flow slows down and heavier particles sink and form a sludge at the bottom, while clarified water exits from the top. This step reduces the SS by 50 until 70% and BOD by 25 until 40%. The tank can be rectangular for lower cost and longer retention time, or circular for easier sludge removal.
The primary sedimentation stage is to be done in a sedimentation tank, where its design is generally a rectangular sedimentation tank. This design of the tank uses a horizontal flow system where wastewater flows from one end to another, which makes it efficient for arranging multiple treatments side by side. Baffles or barrier plates are installed to reduce turbulence and distribute the flow evenly, where at last sediment will settle at the bottom as sludge. The tank design is determined using the surface area equation, which is area equals to wastewater flow per surface overflow rate. And commonly, the tank is designed with a length to width ratio of 3 to 1 until 5 to 1, with a depth of 2.5 to 4 meters, and flow velocity is maintained at 20 to 40 centimeter per minute. The sedimentation tank is divided into four functional zones. The first one is inlet zone, where it is used to ensure incoming wastewater to be distributed evenly across the tank. Second is settling zone, where it is used to clarify suspended solids. Next is sludge zones, where solids will be collected and removed for the next treatment. And lastly is outlet zone, where water is finally removed from floating particles and to be discharged. Next, retention time or hydraulic retention time, which is the average time wastewater remains inside the tank to allow particles to settle effectively. The equation is written as hydraulic retention time equal to flow rate per the volume of basin. For rectangular tanks, the equation can also be written as retention times equal to the length of the basin times the breadth or width of the basin times the height of the basin per flow rate. Tank sedimentation itself usually requires 4 to 8 hours, while coagulated sedimentation only needs around 1 to 4 hours because coagulation forms larger flocks that settle faster. Colloidal particles carry electrical charges so that they cannot settle effectively by the gravity alone. Therefore, Coagulation is needed to combine small particles into larger flocks and improve sedimentation efficiency.
Now, let's talk about the secondary wastewater treatment. From the case, the wastewater has COD number more than 2000 ppm and BOD number more than 4000 mg per liter. Since this wastewater can be considered as a high strength wastewater, anaerobic treatment is preferable than the aerobic one. In anaerobic treatment, anaerobic microbes will convert the organic pollutants into energy rich methane gas. There are some advantages of choosing anaerobic treatment, such as high energy efficiency, since there is no massive electrical need for aeration, produces less biological sludge, and able to handle more volumetric loading rates. There are four steps in the anaerobic biochemical reactions. First, hydrolysis itself is a conversion of complex compounds into soluble compounds. The conversion is done by extracellular enzymes from hydrolytic anaerobic bacteria, which can be facultative and obligatory anaerobic bacteria. For example, like Aerobacter and Pseudomonas. From chemical perspective, hydrolysis is a step where high molecular weight molecules are broken down into constituent monomers. The reaction shows the hydrolysis of polysaccharide, where it is hydrolyzed and becomes the glucose. Second is acidogenesis, where the further degradation happens through fermentation that can break the soluble monomers into even simpler compounds. Chemically, the simpler compounds can be volatile fatty acids, alcohol, hydrogen gas, and carbon dioxide. The fermentation is done by bacteria, and the activity rapidly increases, and there's a potential drop in pH along the fermentation. From the chemical reaction, we also can see that the glucose is broken down into butyric acid, carbon dioxide, and hydrogen.
For the third reaction is called acetogenesis. Following hydrolysis, this reaction is a fermentation of soluble monomer starch. Acetogenic bacteria degrade them into volatile fatty acids, alcohols, H2 and CO2. Rapid bacterial activity also increase and a potential drop in pH. For the reactions, it shows that one compound of butyric acid reacts with water and is converted into two acetate compounds and hydrogen gas. The hydrogen produced will later be used by methanogenic microorganisms during methane formation. For the fourth reactions is called methanogenesis. It is the final terminal phase driven by specialized methanogenic archaea thriving in oxygen-free environments. They transform hydrogen, carbon dioxide, and acetic acid into high-energy methane gas. The first pathway is acetoclastic methanogenesis. This means acetic acid is broken down into methane gas and carbon dioxide. This pathway contributes around 60 until 70% of methane production. The second pathway is hydrogenotropic methanogenesis. Here, hydrogen reacts with carbon dioxide to produce methane and water. Together, these reactions are responsible for biogas formation. For the reactor configuration, the most suitable reactor for this case is the upflow anaerobic sludge blanket or UASB reactor. This reactor is widely used for treating wastewater with high organic content, especially in the food industry. The working principle of the UASB reactor is based on an upward flow system. Wastewater enters from the bottom and flows upward through a dense sludge bed. During this process, microorganisms inside the sludge break down organic compounds. Biomass contact occurs naturally because of the movement of the gas bubbles. So the system does not require mechanical aeration, making it more energy efficient. Inside the reactor, there's a layered granular sludge structure. The outer layer contains hydrolytic and acidogenic bacteria that break down complex organic materials into simpler compounds. Meanwhile, the inner core contains methanogenic microorganisms that convert these compounds into methane and carbon dioxide. The dense granules also help prevent biomass washout and improve sludge stability. At the top of the reactor, there's a three-phase separator of gas-liquid-solid separator, also called GLSS. This component separates the treated effluent, biogas, and sludge granules. The clean water exits from the top. Methane gas is collected as biogas for energy production, and the sludge granules are returned back into the digestion zones for continuous treatment.
After the secondary stage, we move into the next stage, which is the tertiary wastewater treatment. Tertiary wastewater treatment is an advanced purification phase designed to remove the pollutants that are resistant to both primary physical process and secondary biological degradation. The aim of this stage is the removal of stable colloids nutrients and heavy metal residue to achieve solid removal efficiency approaching 100% and BOD reduction up to 99%. These are two of three methods that is used in tertiary wastewater treatment, which are coagulation and flocculation. Coagulation is a process of flocculating colloidal particles in wastewater by adding chemical or coagulants that are rapidly mixed for a short period of time. Flocculation is a slow mixing process that causes floc particles to aggregate and increase in size. First stage, coagulant that has ionic charge opposite to the wastewater neutralizes the negative charge of colloidal particles to achieve electrical neutrality. Second stage, absorption of ions or polymer between the coagulant and the wastewater, which carry opposite charge, can lead to particle destabilization. Third stage, absorption creates bridges between the particle surface, allowing aggregates to be formed. Fourth stage, the aggregates will combine to form larger flocks. Fifth stage, sweep coagulation or flocculation, which colloidal particles settle and are removed from the suspension as they are trapped by the floc growth. The coagulant used in this case is FeCl3 or ferric chloride. Ferric chloride that has added to the wastewater undergoes hydrolysis and forms an insoluble hydroxide or ferric hydroxide that will trap colloidal particles and dissolve organic matter in wastewater or called sweep flocculation. These are the chemical reaction when ferric chloride added into wastewater as the coagulant agent. This reaction happens in the pH of 7, ideal pH, for the coagulation process because the hydrolysis of ferric chloride results in optimal ferric hydroxide formation while maintaining a pH level that is safe for aquatic species. If ferric chloride is too low, it will fail to destabilize the colloidal particles, and if ferric chloride is too high, the suspended particle will become stabilized and the zeta potential will deviate from zero, which they begin to repel each other again. Even though the charge has flipped, the result is the same as before you added any coagulant.
So the next stage of the tertiary wastewater treatment is chemical precipitation. Chemical precipitation is the process of converting dissolved or suspended pollutants into a solid phase called sediment to facilitate their separation from the liquid phase by using polymers. The principal are polymers which has cationic or non-ionic interact electrostatically or mechanically to aggregate small particles into large blocks. The polymers also called chemical precipitants, and in this case we use lime to perform metal peroxide precipitation. The principle of lime treatment is raising the pH to convert dissolved hardness, which is calcium and magnesium, into solid precipitates that can be physically separated so that they are going to be a sediment. The purpose of this precipitation is to precipitate calcium and magnesium with the reaction calcium at pH 9.5 to 10 and reaction with magnesium at pH 10.5. The lime treatment begins with a series of rapid mixing, flocculation, and sedimentation stages. During flocculation stage, the flocculator that used is divided into several compartments, with progressively decreasing agitation intensity before the mixture finally enters the sedimentation stage. This sun treatment has low detention time to remove calcium and magnesium ion on wastewater, which is around 15 minutes, to show significant results.
These are the advantage and disadvantage of tertiary wastewater treatment. The advantage is first, effective at removing non-biodegradable contaminant, capable of significantly reducing chemical oxygen demand or COD levels, produce heavy flux that act as sweeping agent, accelerating the precipitation of calcium carbonate, produce very clear effluent with a shorter retention time compared to biological treatment system. The use of lime enables maximum efficiency in the removal of calcium and magnesium in just 15 minutes, and neutralize the acidic nature of ferric chloride to minimize the corrosive effects on equipment.
Next are the disadvantages. This chemical process has several disadvantages. First is the iron compounds present in the wastewater are corrosive to piping and tank infrastructure and have a low solubility. Soluble metal residues pose a risk of contaminating aquatic ecosystem when discharged into the environment. Excessive lead addition during the precipitation can actually increase the total dissolved solids and hardness level of the wastewater, which is not good for the environment as well. Not suitable for wastewater with very high concentration of heavy metals. Produce large volumes of sludge with high moisture content, making the drying process difficult, and the last is large sludge volumes increase treatment and disposal costs through third-party providers.
This is the flowchart of the overall wastewater treatment process. It starts with primary wastewater treatment, where sludge is the output. Then the sludge is processed into secondary treatment into biogas. Last, the biogas get into the tertiary treatment and produces solid sediment as the final product. In conclusion, wastewater treatment consists of primary, secondary, and tertiary stages to improve wastewater quality before discharge. Primary treatment removes suspended solids through screening and sedimentation with a retention time of 4 to 8 hours. Secondary treatment uses an anaerobic system to convert organic compounds into biogas through hydrolysis, acidogenesis, acetogenesis, and methanogenesis. Lastly, tertiary treatment applies coagulation, flocculation, and chemical precipitation using FeCl3 and lime to remove colloids and heavy metals. Overall, selecting the proper treatment system is important to ensure effective and environmentally safe wastewater management.